Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I'm your host, the Dabbling Doggo.
I dabble.
Last week, we learned about searching and sorting algorithms, and then we learned about programming efficiency. Today, we'll begin to look under the hood of Julia to get a better understanding of how it works. The concepts included in today's tutorial are based on the following YouTube videos. 1. Introduction to Julia Internals by Jeff Bezanson in 2014, and 2. A Practical Introduction to Metaprogramming in Julia by Andy Ferris in 2018. I will be providing a high-level summary of the concepts presented in their presentations. For more detailed information on these concepts, please watch their videos. The links are provided in the description below. If you want to design a new programming language, what would you need? You would need a front end. The front end is the syntax and semantics of a language that a user would need to express their thoughts in text form. You would need a back end. The back end is the actual machine code that your computer can understand and execute. And you would need a mystery box. That mystery box is what converts your human-readable text file into something a computer can comprehend. For many programming languages, the mystery box is something called a compiler. Designing the front end is the fun part. The front end is the high-level programming language that users actually see and interact with to generate their source code. Users are often very passionate about what they love or what they hate about the language, and language designers love to interface with their users to improve their experience. Designing the back end is the boring part. This is the part that users don't see and often don't understand. Not only do you need to interface with your own computer, you also need to interface with all known computer architectures and operating systems, since they all have their own versions of native machine code. Designing the compiler is a thankless job, yet without a compiler, there's no programming language. Depending on the language, this is a part that some users may see, but often don't understand and don't appreciate. Historically, compilers were written by the creators of the programming language and were specific to that language, since every programming language has unique compiling needs. Creating a compiler is not glamorous work, and it's difficult to perform, so talented compiler engineers are in short supply. So while you may have a great idea for a cool new programming language, you will ultimately run into this bottleneck of what to do when it comes time to compile your code. The LLVM project changed all of that. The LLVM project started in 2000 at the University of Illinois at Urbana-Champaign under the direction of Vikram Advi and Chris Lattner. The concept behind the LLVM project was to standardize and to optimize the compilation process and to make its code open source so that it could be used by any programming language and it could interface with any computer hardware and any operating system. LLVM solved the problem of having a unique compiler for every programming language by creating a new, universal, intermediate language. Now, programming language designers would not need to figure out how to lower their code all the way down to native machine code. Nor would they have to worry about keeping up with all the changes that are happening at the CPU manufacturers or the operating system providers. All they would need to do is figure out how to lower their code part of the way to something that LLVM could understand, and then LLVM would take it from there. LLVM is a massive programming language compiler infrastructure project that solves the problem of having to find compiler engineers to design and maintain the compiler and the backend. Having LLVM in place frees up front-end designers to just create cool new programming languages and to focus on interfacing with their users. In 2005, Chris Lattner left the LLVM project to join Apple to bring LLVM up to production quality for use in Apple products. In 2010, he began work on developing the Swift programming language for Apple. Swift was officially released to the public in 2014. Today, the Swift programming language is the preferred programming language used internally at Apple and used externally by developers for applications for Apple products. As you might have guessed, Swift sits on top of the LLVM infrastructure. Another notable user of the LLVM infrastructure is Julia. Since both Swift and Julia use the same LLVM compiler infrastructure, you would think that Swift and Julia would have the same performance. Swift has a reputation as being an easy-to-use language for developing apps for Apple products. However, it doesn't have a reputation for speed, while Julia does. There's clearly something going on in the front end of Julia that differentiates it from other languages, like Swift, that also use the LLVM compiler technology. In order to answer the question of how Julia works, we need to look at the question in two parts. 1. How does Julia work as the front end? And 2. How does LLVM work as the compiler and the back end? At a very high level, here's what happens when you hit enter after typing in some code into the REPL. As soon as you hit enter, Julia begins the process of lowering your source code text from a high-level programming language to native machine code. This process is a multi-step adventure and not an instantaneous conversion. The first step is to convert your source code text from a collection of characters into something called a Surface Syntax Abstract Syntax Tree, or an AST. The AST is composed almost entirely of a new data type called an expression. The AST is a compact, structured representation of the source code that contains only the essential information. There's another event that happens as soon as you hit enter called macro expand. I'm going to skip this event for now, since I'm going to cover macros in next week's tutorial. Julia then takes the AST and unwraps it further through a series of syntactical transformations. This is the stage where syntactic sugar is removed, control flow is broken down into clear linear steps, and scopes are resolved between global and local. The result is a transformed code called an intermediate representation. An intermediate representation, or IR, is code that is at a lower level than the original source code, but at a higher level than native machine code. As a result, the IR is more difficult for humans to understand, and it's still not readable by your computer. However, the IR is easier to optimize, and LLVM requires an IR as an input. At this point, the IR still resembles Julia code. This is where the magic happens. This stage is one of the secrets of Julia that other languages have not been able to duplicate. During this stage, Julia infers which types to pass to the compiler. Julia also optimizes your code so that the code that it passes on is as efficient as possible. This inference and optimization engine is one of the key ingredients which allows Julia to be both flexible and fast. Julia's algorithm automates this task so that users can focus on expressing their ideas in human-readable form, while Julia takes care of the translation and the optimization. The result is a further lowered IR, which is then handed off to LLVM. This is the last time that the IR will resemble Julia code. LLVM takes the lowered and optimized Julia IR as its input and then goes through its own compiler optimization process. The result is an even further optimized, further lowered IR called LLVM code, which is an IR one step above native machine code. The LLVM code is a universal IR and does not depend on any specific programming language at the front end, nor any specific computer architecture or operating system at the back end. At this point, the IR is no longer recognizable as Julia code. LLVM then converts the LLVM code into native machine code, which allows your computer to understand and execute your original source code. The native machine code is specific to your computer's architecture and operating system. Once the native machine code has been generated, your original source code is set to be compiled. Once compiled, Julia stores the native machine code in your computer's memory and returns the appropriate response to the REPL. Julia only needs to compile your source code once per session. I'm not sure if you've ever noticed, but there's a slight delay the first time you call a new function. However, the second time you call that same function, there's no delay. Let's take a look at a function that we learned in tutorial number 6. Today, I'll be using just the REPL and not Atom. I'll speed up the typing since you've already seen this code. Now, watch closely to what happens after I hit enter. Did you catch it? There was a slight delay. Now watch it again as I call the same function using different arguments. See, there was no delay this time. That's because the first time you call a new function, Julia goes through all of these steps to compile the source code for that function. Once it's been compiled, the native machine code is stored in your computer's memory, so Julia doesn't need to compile it again the next time you call it. Let's go through a simple example of 1 plus 1 and follow its journey as it gets lowered from source code to native machine code. In your REPL, type in 1 plus 1 and hit enter. In that split second between the time you hit enter and just before the number 2 appeared, your source code went on a multi-step adventure. The first thing that happened as soon as you hit enter was that 1 plus 1 was parsed into a surface syntax AST consisting of an expression. You can see what that expression looks like by using the meta.parse function. Meta is a hidden module with its own functions, one of which is meta.parse, which converts a string into an expression. Meta.parse should not be confused with the built-in parse function in base Julia that we use to convert a string into a number in an earlier tutorial. Note that the argument to the meta.parse function was entered as a string. The result looks like a symbol due to the colon, but the result is actually a new data type called an expression. You can confirm the data type of the expression by using the typeof function. You can confirm that whitespace doesn't matter by experimenting with the whitespace in between the quotes. You get the same expression because Julia is discarding any unnecessary syntax and only keeping the bare essentials. The expression is a container that holds the important pieces of your source code, which makes it easier for Julia to understand. You can see the contents of that container by using the dump function. The expression contains two sections, a head and some arguments. The head is a function call command that is listed as type symbol, while the arguments are listed as a 3-element array containing the arguments plus 1 and 1, with data types symbol, int64, and int64 respectively. Here's what the expression looks like as an abstract syntax tree. If you wanted to, you could have created your own expression by using the expr constructor. You get the same expression. The first element is the head, which is entered as type symbol. The rest of the elements make up the arguments. Arguments are listed as either symbols or numbers. You can confirm the data type of this expression by using the typeof function. You can view the contents of this expression by using the dump function. You can confirm that the first expression and the second expression are the same by using the equality test. Interestingly, because the expression is a container that holds data, you can index the various elements just like a data structure. We'll explore the implications of this in greater detail in next week's tutorial. Once your source code has been parsed, it's ready to be lowered. You can see what your lowered code looks like by using the @code_lowered macro. Base.add_int is a base primitive function that adds two integers together. This code is called an intermediate representation, or IR. Although it may be more verbose than either the original source code or the AST, it still resembles Julia code and is still readable. The next step is to infer types while also optimizing the code. You can see the resulting IR by using the @code_typed macro. In this simple example, nothing much happened between step 2 and step 3. All it did in step 3 was to add type int64 to the IR. This is the last time that the IR will resemble Julia code. This is the IR that Julia hands off to LLVM. After LLVM receives this IR from Julia, LLVM goes through its own compiler optimization process and then generates its own LLVM IR. You can see the LLVM IR by using the @code_LLVM macro. At this point, the IR no longer looks like Julia code. However, in this simple example, you can still see that this IR is adding two 64-bit integers together. This is the IR that LLVM feeds into the compiler. This is the final step. You can take a look at the native machine code by using the @code_native macro. Technically, what you're seeing is assembly code, which is a human-readable form of machine code. Machine code is just zeros and ones. Machine code and assembly code are essentially the same thing to your computer. This is the code that your computer understands. This code doesn't resemble either Julia or LLVM. It is merely a list of primitive commands that your computer will execute in sequence. I'm using a Windows PC with an Intel CPU that uses an x86-64 architecture. If you're using a different setup, your native machine code may look different. This low-level code may look complicated, but with some effort, we can understand what it says. The top few lines and the bottom few lines are equivalent to begin and end. LEAQ is the actual instruction that your CPU is executing. LEA stands for Load Effective Address. In our case, it's telling the computer to add 1 and 1. The suffix Q indicates 64 bits. The percent signs, used as a prefix, indicate memory register names. If you think about it, following this code-lowering journey is like traveling back in time to the early days of computing. Before there were high-level programming languages, the pioneers of computing would program their computers using a language similar to the code that you're seeing at the code-native level. While this simple example isn't too bad to understand, just imagine trying to write a large program using this low-level language. This is just another reminder that we are truly living in the future, which is only made possible because we stand on the shoulder of giants. Now that we have a feel for the lowering process and know the tools that we can use to view the lowered code, let's take a look at another, slightly more complex example. Let's take a look at the function f of x equals x squared. Don't forget to use the quotation marks. So far, nothing surprising yet. At this step, Julia has inserted the function called base.literal_power, which is the built-in function to calculate the power of a number. This is the IR that Julia uses to infer types and perform optimizations. Something very interesting just happened. Did you catch it? Julia actually changed the code. Rather than calling for 2 squared, like you asked in your source code, Julia is now calling for 2 times 2. Why would Julia do that? Well, this is an example of optimization. Julia is smart enough to know that 2 times 2 and 2 squared will give you the same answer. Julia also knows that it's faster for your computer to calculate 2 times 2 rather than 2 squared, since 2 times 2 is using a more primitive operation. In order to give you the fastest performance, Julia will go through your code and automatically optimize it for you. It's like having the smart kid in your class check your homework before you hand it in. Pretty wild, right?
Wow!
This is the IR that's handed off to LLVM. This IR no longer looks like Julia code, but you can tell that it's multiplying two 64-bit integers together. This is the IR that LLVM feeds into the compiler. You can disregard most of this code and just look at the line that begins with IMULQ. IMUL means signed multiply, and the Q suffix indicates 64 bits. Note that there's only one register location called %RAX. That's the memory location where my computer has stored the 64-bit integer 2, and that line is telling my computer to multiply 2 by itself. It's fascinating to see how much is going on under the hood. By the time the entire process unwraps our simple code, it's been transformed into a longer, more primitive version of the code in a language that your computer can understand. While we may not always understand all of the code in the interim steps, it's important to point out that the lowering process is a fully transparent process which can be examined at any stage along the way. It's not a black box. Knowing how Julia takes your inputs from source code to native machine code will make you a better programmer. If you've ever thought, I wonder how Julia did that, now you have some tools to dig into it. You can improve your program's performance by writing type-stable code. Code is set to be type-stable if the type of every variable does not change over time. For example, if a function takes an argument of type int64, then all calculations and results must be of type int64. If at any point the calculations or results change to a float64, for example, the function is set to be type unstable. Functions that are type stable will get the best performance. This is why the division operator always returns the type float, even if you divide two integers that should normally result in another integer. In this case, an integer divided by an integer should result in another integer. However, that's not always true. 5 and 2 are both integers, but if you divide 5 by 2, then you get 2.5, which is a floating point number. It's not good to have a function that returns values of types that are different than the input types. In order to ensure that the division operator is type stable, Julia converts the inputs to type float64 so that the input types and the output types are always the same. Wow, that's a lot of heavy concepts to cover. Let's turn back the clock and revisit the diagram from the beginning of the tutorial to see if it makes any sense now. For a generic programming language, the mystery box in the middle is a black box called a compiler. The compiler performs the thankless task of converting a user's source code into native machine code. However, because it's a black box, there's no way to see what it's doing. In the case of Julia, the mystery box is a lot more complex. The mystery box is actually a glass box that's split into two halves. The first half is unique to Julia, and the second half is common to any programming language that uses LLVM. There's no mystery as to what's happening anywhere in the process, since the user can see how the original source code is being transformed into native machine code at any stage of the process. Optimization is happening in both halves, so the resulting native machine code is as efficient as possible. Well, that's it for now. Today, we began to look under the hood of Julia to get a better understanding of how it works. Next week, we'll continue to explore Julia under the hood by learning about metaprogramming and macros. If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. New tutorials are posted on Sundays. If you have any questions, please post them in the comments below. Feel free to spread the word by sharing this video, since I'm sure you'll all agree that this is the finest tutorial on all of YouTube.
Worst tutorial ever.